Hello again. We're going to this time solve problem 1.30 out of the textbook. This problem asks or states the rigid bar ABC shown in figure is supported by the pin at the bracket A and by a tie rod 1. Tie rod 1 has a diameter of 5 millimeters and is supported by the double shear pin connections at B and D. The pin at bracket A is a single shear connection and all the pins are 7 millimeters in diameter. So assume A, which is here, so this is A, is 600 millimeters, and B is 300 millimeters, and H is 450 millimeters. The force P, which is this, is 900 newtons, and this angle theta is 55 degrees. So we need to determine the normal stress in rod 1, the shear stress in pin B, and the shear stress in pin A. The normal stress in rod 1, right? So if I just get this and say the normal stress in rod 1, this is rod 1. The shear stress in pin B, which is here, and the shear stress in pin A, which is here. Okay? So really, we don't need anything up here. We can just neglect that, right? So what I'll do is I'll draw a free body diagram. That's the first thing that I always like to do. Our given information here, we already determined our distances, where they are, and B and A and everything. So the first thing that we can do now is just draw a free body diagram. I'm going to just draw a line with force P that I'll put as 900 newtons. And that's 55 degrees below the horizontal. I have, because this is point A is a pin connection, we're going to have a reaction in the Y. So that's RAY. A reaction in the X, that's RAX. And then this rod 1, one thing I want to call to your attention is rod 1, there's something special about this, a unique thing that we call it. It's a two-force member. And a two-force member, we want to make sure that we know that this force that's acting from B is acting along that rod. That force is acting along the rod. So it's acting at the same angle as the rod, right? And this angle, I'll call it phi. And this is force F. Is pointing up there. So we have four unknowns in this. We have F, phi, the reaction in the Y direction, and the reaction in the X direction. So the first thing that I want to do is maybe solve for this angle here in phi. And looking at our actual diagram here, this distance here and this distance here, if we look at the triangle, well, it's maybe if I clean this up a little bit, the distance here from A to D is 450 millimeters, and from A to B, right, so this little a is 600 millimeters. So we could use our knowledge of trig and say, well, if this is phi, we could say opposite over adjacent, right? So that's tangent phi equals opposite over adjacent. Phi equals tan inverse opposite over adjacent. So phi equals tan inverse of 450 divided by 600. So I get a degree measurement of 36.869898 degrees. So this angle measurement here is then going to be up here for phi, right? So now we can go ahead and start solving for these forces. Now we know phi, there's three forces here that are unknown, which is convenient because three equations, some of the moments in the X, some of the moments in the Y, or I'm sorry, sum of the forces in the x, sum of the forces in the y, and then sum of the moments, right? So 3 equations, 3 unknowns. Now, where do we sum and what do we do first, right? Well, just a good habit to get into is trying to eliminate as many forces that we can at once, right? So if we sum our moments about point A, the moment arm is 0 for both RAX and RAY. So the only force that we'd be left with are the, say, vertical forces here for F and at this point B, this is B and this is C. So what I'm going to do is these forces, I'm going to break them up into components, right? And so this component here, there's a vertical force here, so it's F sine of 36 point, we'll call it 9 degrees. Oops. And then there's a horizontal force here going this way of F cosine of 36.9. Then there's a vertical force here of 900 sine of 55, and then a horizontal here of 900 cosine of 55. Okay, so now we can sum our moments around point A. Sum the moments at A equals 0, identifying that this counterclockwise will be our positive direction. So every force in the counterclockwise direction, which is our F sine of 36.9 degrees, (600 millimeters) minus, and then 900 sine 55 multiplied to the radial arm, which is again A plus B, which is 600 plus 300, so 900, and then that equals 0. So now we can solve for F. F equals 900, what's that, newtons, multiplied to 900 millimeters sine 55 divided by 600 millimeters sine of 36.9. Okay, so I get a force at pin, or at B, force equals 1,841.8 newtons. So now we can go ahead and solve for the rest of the reaction forces. We solved for F, right? So that's F, and now we can solve for either RAY or RAX. I'm going to go ahead and sum the forces in the Y first. It doesn't matter at this point, you can do either or first. Sum of the forces in the Y equals 0, positive direction being up. So we'll have RAY plus F sine 36.9 minus 900 sine of 55 equals 0. And I get RAY to equal a negative. RAY equals a negative 368.618 newtons. Now, what that means is it doesn't mean that we're wrong, that just means we assumed wrong. So when I drew my free body diagram here, I assumed RAY to be going in this direction, right? That was a wrong assumption. So what RAY is really doing is going down, okay? So what I'll do is just write this as RAY equals 368.6, we'll call it 2 newtons going down. Okay. So the next force we'll do is sum of the forces in the X equals, let me zoom out here. Sum of the forces in the X equals 0, going this direction is my positive, so RAX minus F cosine of 36.9 plus 900 cosine of 55 equals 0. So I get a force here of RAX equals 950 56.64 newtons. Okay, so now what, right? So now we found our force at point B, right? So this is along the member, this is in the force in member 1. This is our reaction force RAY, and this is our reaction force RAX. So we need the magnitude of the resultant force for the pin at A. So the magnitude of the resultant force, right? So the force at A is going to equal the square root of AX squared plus AY squared. So A equals sum of 368.62 newtons squared plus 956.64 squared. And I get a resultant force FA equals 1025.2 newtons. Okay, so now we can actually solve a couple of these questions that were the original questions. We're not done. We just did the initial work. All this work was just to find the forces so that we could actually answer the question. If I zoom in again here, it says solve for the normal stress in rod 1, shear stress in pin B, and the shear stress in pin A, right? So a couple of things we need to remember also is go back over our problem statement. We need to remember that all of the pins, right, all pins are 7 millimeters in diameter. And the pin at bracket A is shingle shear connection, and the pins B and D are double shear connections. Okay, so let's do the first part, which is finding the normal stress. So part A, find the normal stress in rod 1, which is F over A. So the normal stress, which is the force we found in rod 1, which is going to be 1841.8 newtons, divided by the area of rod 1, which the area of rod 1 is has a diameter of 5 millimeters. So we'll do pi over 4 multiplied to 5 millimeters squared, and that'll give us the stress at in rod 1. So I get a stress in rod 1 of 93.8 megapascals. And if you're confused on how I got these units, I suggest you look on the unit sheet that it has been posted on Blackboard. So part B. Now we're looking for the shear stress in pin A. Or I'm sorry, the shear stress in pin B. So the shear stress in pin B, which is tau, equals shear over area. So the shear is going to be the same force that was the force that was applied to in the rod. So tau is going to equal 1841.8 newtons divided by the area of the pin, right? So the area is going to be pi over 4 multiplied to, the pins are 7 millimeters squared. But we need to multiply it to 2 because it's a double shear connection, right? So there's 2 of them, right? So I get a shear of 23.93 megapascals, right? That's for part B. So then I'm going to go over here and do part C. So now we're looking for the shear at A. This was shear at B, and rod 1 equals V over A. So the shear in pin A is going to equal the force, the resultant force that we found at A, which is 1025.2 newtons divided by the area of the pin, which is again 7 millimeters. So pi over 4 multiplied to 7 millimeters squared. And we do not multiply this because this pin is in single shear, so we don't multiply by 2. So I get a shear at A equals 26.64 megapascals.